Okay, good. So the recording has started. Let's minimize this. All right, so let's look at the, yeah, so we were looking at commitments from without using one-way functions, right? So here, so in class, we already discussed this classical scheme where the receiver samples eta, uniformly random string of length 3n, sends it to the sender samples a seed for the pseudorandom generator, which is of n bits, and it sends this state as the commitment, GOS O plus eta to the B. And so that's the commit phase. And then the opening was that the sender sends the seed S together with the bit B that was committed. Right? And the receiver is going to check whether the seed actually matches. So if the commitment can be reproduced by running the pseudorandom generator on the seed and XORing it with the randomness that was selected by the receiver in the beginning, right? Okay. And we already argued what the intuition for the security was, right? So we said that hiding is obvious just from the fact that a pseudorandom generator is indistinguishable from a random state, so from a random distribution, as long as S is hid, which is the case. Hiding is trivial, but it's computational. And then we argued that binding is statistical. So this we already saw last time, so I'll not spend too much time on this. Now what we're going to do is we're going to generalize this construction. And here's the idea. The idea is to replace the pseudorandom generator with a pseudorandom state, okay, which is phi sub k. And we're going to replace addition of eta to the B using the one-time pad, okay? So one-time pad is randomly applying X and Z. So eta to the B, essentially acts like a one-time pad, right? Because you're XORing with the random string. So we're going to do the same thing here. So the construction is as follows. The sender prepares psi sub B. And so B is the bit that they want to encrypt. And they start with a pseudorandom state on m qubits, okay? And they are holding, so whether or not they apply B would be encoded by applying the one-time pad, which is X to the X and Z to the Z. And the key is held in the R register for the one-time pad and for the pseudorandom state here. And then register C is sent to the receiver. And suppose, oh, sorry. Okay. Right. And when you do the opening, you send register R, right? So this is the commit phase, sending register C, and then the opening phase would be sending register R. Okay. And together with the bit B, I guess. Okay, so then we note that by the end of the commit phase, right, the receiver state is going to be the following. So it's if B was committed, then row 0 would be this state. And if B equals 0 was committed, then this is the state you'll get. And if B equals 1 was committed, then this is the state you get, right? So it's the same except that you add the Pauli pad. I should have put 1. I don't know why I put B here. Okay, and now the hiding property essentially follows from the security of a single copy secure PRG or PRSG, right? So random secure generator. So intuitively, what this means is that if I give you one copy of a state produced using this pseudorandom generator, where the key K is uniformly chosen, and I don't tell you the key, then the state is for a computationally bounded adversary or observer independent of, indistinguishable from the identity, the maximally mixed state. And so that is for row 0. And then for row 1, from the property of the quantum one-time pad, which we'll see in a moment, the state, regardless of what state you have inside, once you apply the quantum one-time pad, it becomes indistinguishable from the maximally mixed state as long as the keys are hidden, which they are during the commit phase, from the point of view of the receiver. Okay, so it's clear that rho 0 and rho 1 are computationally indistinguishable, which establishes hiding. Now we establish what is called statistical sum binding. Okay, so the claim is that to show the binding property in the quantum setting, it suffices to show that the fidelity between rho 0 and rho 1 is negligible. Okay. So we look at how that proof goes. But statistical sum binding basically says that the probability, so yeah, it says here, so suppose P sub B is the probability, the probability with which the malicious sender, let's say, can convince the receiver or can open and give a valid copy to B. So suppose PB is this probability, right? So sum binding is basically trying to say that what is the bound you can give on P0 and P1. P0 plus P1 should be at most 1. Right? You should not be able to convince the verifier of both outcomes. You can only do one. Okay. And it turns out that this is the right notion. Why this is the right notion, I guess we'll see in probably slightly later lectures. It has to do with the fact that we want to be able to build, so from commitments, so commitments plus communication implies OT, oblivious transfer, and that in turn implies multi-party, or at least two-party communication. So this is what we, so the notion of commitments that is needed to give this implication is sum binding. Okay, and we'll hopefully look at this this construction as well, because this is also a relatively recent result. Okay, so where were we? Yeah, so we wanted to see whether rho 0 and rho 1 have negligible fidelity, right? So it turns out that to establish this, that this sum is at most 1. It suffices to show that rho 0 and rho 1 have negligible fidelity, and so for the statistical case, and the way this is done intuitively is as follows. So rho 0 is a superposition over 5Ks, right? And this is at most 2 to the n-dimensional space. While rho 1, so I think it has support on 2 to the n-dimensional space, right? Because there's only as many independent directions that we're exploring. While rho 1 has support on essentially the entire 2 to the m-dimensional space, where m is greater than c and nc is 1. So the overlap tends to be exponentially small if we look at the formal statements. Yeah, okay, so that completes the first little part. Let's move on to the next part. All right, so here's the notation that we use. Okay, so the notation we use is as follows. Oh, okay, I actually skipped that. So this is just using standard crypto and quantum. So we're very familiar with the notation that's being used. The only interesting thing that we want here is the statement that I mentioned about the one-time pad. So if you XOR with x to the x, z, z, z to the z, x, x, if you conjugate with these matrices overall x and z for m dimension, where rho is an m-qubit state, you'll get identity times m by 2 to the m. This follows from direct calculation. Sorry, so yeah, we get Okay. All right, so let's resume. So the definition of a pseudorandom quantum state generator is as follows. So a pseudorandom quantum state generator is a QPT algorithm state gen that on input k of length n outputs an m qubit state phi sub k, satisfies the following property. The property is that for any polynomial t and any non-uniform quantum polytime adversary a, there exists a negligible function such that the difference between these two is negligible. And what are these two things? In one case, you're given t copies of the pseudorandom state. The other case, you're given t copies of a high random state. Okay, and the pseudorandom state is sampled, so it's a family of states, right? Keyed family of states, and the key is sampled uniformly, and the key is of length n, while the state is of length m. So that's the difference has to be negligible. Okay. And there are some remarks. So in the most general case, state gen can be thought of as the following algorithms. On input k, it first produces a classical description of a unitary circuit, U sub k, then it applies U sub k on the all zero states, all zero state, and then obtains phi sub k. This is the phi sub k state, which is and then oh yeah, so which is UK acting on all zeros, and then the output is this phi k state, basically register A, right? So you remove register B, whatever is left is what you call rho sub k. Okay, and then rho sub k is on an average almost pure. Okay, and why is that? So one can see this. So suppose that you do the following. So you start with an adversary A that runs the swap test on two copies of the received state and outputs the result of the test. Okay, so recall the swap test is the following. So you start with 0, you apply the Hadamard, and then these are the two states that you're going to swap and test. So let's call them sin phi. So you apply this control double swap. Forget what this is called. Maybe Toffoli, is it? I don't remember. Okay. And then you apply the Hadamard, and then you do the measurement. And it turns out you can do the calculation quickly and check that the probability of getting a 0 here is related to the overlap between psi and phi. Okay. So now, if you have rho sub k, t many copies of it for a uniform k, then the probability that A outputs 1 is 1 plus 1 by 2 to the n, sum over k, trace rho square k, because you can check this. And when you take t copies of the Haas state, right, the output that A outputs, the probability that A outputs 1 is exactly 1, because this overlap is exactly 1, right, because they're all the same. And so what that means is that this quantity must also be essentially 1. Otherwise, it doesn't end up. Sorry, so this entire quantity. So that basically says is that the quantity has to be rho k has to be pure, which means that rho k is is a pure state essentially. Okay, so why is he explaining all of this? Sorry, why is the paper explaining all of this? They're explaining all of this because in this work, they are going to assume that the state that is output by the pseudorandom generator is pure, and they'll denote it by phi sub k. And they claim that the result also holds even if the state is arbitrarily close to, is negligibly close to pure. And because they're making the assumption that it's a pure state, the state produced is pure on A and B, and they assume that oh, sorry. Okay, so the state has to be pure on system A, right? That's what we said here because it was A, B, right? You traced out B and you were sending A. They changed the register names. I got a little confused. Right. So they changed the register name, and so okay. So on register A, the state is pure, right? So this phi has to be of the following form, right? It's tensored with pure state on A, and then whatever is on the auxiliary state, you can anyway purify. So it's not a big problem. Okay, so the same result holds even if aux results are present. So aux registers are present. So we're not going to worry too much about the auxiliary registers now. And it's also important to note that the result, Kretschmer's result, which we'll see maybe next time, showed and it gave an oracle separation between pure output and no auxiliary qubits. Okay, and so this is the kind of PRSG, pseudorandom state generator, that was used to show the oracle separation between well, basically they showed that even if BQP equals QMA, you can still have PRSGs. So that's the separation they showed, and the PRSG they used, it was just for pure states and didn't have any auxiliary qubits. And so therefore it suffices in this construction to also use such a PRSG. And in fact, what is needed in this construction is something even weaker. So they just need the security definition to hold for t equals 1, so which is what they call a single copy PRSG, right? Okay, so single copy thing is exactly the same definition, except that now you get a single copy, right? Unsurprising. And the remark is that one could simply use, instead of giving a single copy of psi sampled from the Haar measure, you could simply give it a mixed state. That doesn't change anything, because a single copy of a Haar random state is indistinguishable from identity anyway. It's only when you have multiple copies that things get different from the identity matrix, because you can do swap tests and so on. Okay, and the next remark basically says that that rho k, which was produced by state gen, had to be pure, right? This we saw in the previous remark. But for a single copy, this is not actually true, because first of all, you cannot do the swap test, right? You have only one copy, so it's not clear. And also there's like a trivial construction, right? The state gen operation simply outputs the maximally mixed state. So so therefore, the single copy PRHG case, it is with loss of generality. So you're actually assuming in this construction that the PRHG is such that the state being produced is pure. Okay. There were two small remarks. So the first remark is that a single copy PRSG construction is potentially easier than doing a multi-copy, or the standard PRSG. And one can do a construction essentially from, just assuming a PRG, for example, to begin with. So if you have this PRG01, which stretches n bit input to an m bit output, you basically just output this output of the PRG itself for all k, and the claim is that this will already give you a pseudorandom state, at least as far as one copy is concerned. And one might think, so this is the other remark, that a single copy PRSG, which is producing an output state bigger than the input state, input string, so the number of qubits m is larger than the key length, strictly larger, then shouldn't that also be a PRG, right? Because you can just measure 5k in the computational basis, and this would give you more bits of randomness than you put in. And this seems to contradict Kretschmer, right? Which was saying that PRSGs can exist even if PRGs don't exist, right? And this seems to suggest that PRSGs imply PRGs. But this is not actually true, and the reason is that the process of measurement is non-deterministic, while PRGs are deterministic functions, right? So there's that's the small remark that we wanted to make. All right. So okay. So I think now we can actually start with the formal definitions.